In this video, I'm going to go over cartographic projections, which are the different ways that the round Earth is transformed onto a flat surface. Before I get into projections further, I'm going to play a short video for you guys. This is probably one of my favorite videos, educational videos on the internet ever, of all times. So hopefully you like it.
All right, here we go. If I want to turn this globe into a flat map, I'm gonna have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder's surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa. By a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
The Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
So if you want to see a map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkel triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer. If you yourself want to poke fun at the Mercator projection, you...
Alright. Wasn't that awesome? It was awesome. I know it was the best thing you watched all day. Well, except for me talking, of course. All right. So, map projections are the way in which the 3D Earth is transformed to a 2D format. This is accomplished by taking a light source and shining it through the surface of the Earth onto a different surface to make it two-dimensional. Because projections are models, they will always have some level of distortion. However, the type and severity of distortion is dependent on the methods that were used to create the map. To minimize distortion, you must first take into account the location and spatial extent of the map, as well as the map's purpose. The location of the map is incredibly important because different projections are better for certain areas, as well as the number of projections available. The purpose of the map will help you determine which types of distortions you are willing to sacrifice so that the important measurements are as accurate as possible. Once you decide that will help you determine which surface the map should be projected on, the light source that should be used, its aspect, and its sequencing. When you are working with data, you need to make sure that all of the data sets are in the same projection. If they are not, your map and analysis are going to be incorrect. You have to transform them just like you do with datums. The three primary map projection families are cylindrical, conical, and planar. Planar projections are also sometimes referred to as azimuthal or zenithal. Each of these families are based on the surface that the globe is projected onto, with the exception of the mathematical or conventional projection. Cylindrical projections are projected onto cylinders. Conical projections are projected onto cones, and planar projections are projected onto a flat plane. Mathematical or conventional projections are created with a formula that minimize distortion. However, all maps are the most accurate wherever they touch or intersect with the projection surface. In the image in the slide, the cylindrical projection is the most accurate at the equator. This is where the great circle term that we went over in the previous video was implemented. All of the locations along that great circle are the most accurate, and they become more inaccurate the further they move away from it. In the conic projection, you can see a lighter circle that runs through Canada and Europe, which is a small circle, and the points along that circle are going to be the most accurate. Lastly, we have the planar projection, and it's most accurate at the North Pole because projections only touch the surface of the Earth at that one point. Before I delve further into the different projection families, we need to go over some of the new terminology about the placement of the globe relative to the projection light and surface. Aspect is the orientation or angle of the projection surface in relation to the globe. The three aspects are normal, transverse, and oblique. In a normal projection, the projection surface is parallel to the Earth's axis, or more simply put, it's vertical based on the line drawn between the north and south poles. Transverse projections, however, are oriented perpendicular to the Earth's axis, or horizontal from west to east. Oblique projections are all other orientations that are not normal or transverse. I don't want to make things more complicated for you, but sometimes projections may be classified as equatorial or polar. That's because the projection is touching the globe and is most accurate at the equator or the poles. The normal aspect can be equatorial or polar, and that's because the great circle is the equator in a cylindrical projection, and it touches the poles in a planar projection. In transverse projections, it's the opposite. Cylindrical projections are polar, and planar projections are equatorial. It's also important to know whether the projection surface touches the globe or intersects it. The figure to the left shows the tangent surfaces. Tangent, cylinder, and cones touch the Earth in a circle. The plane touches it at only one point. Secant surfaces, shown on the right, intersect with the globe or cut through it instead of just touch it. The thicker, solid green circles are where each projection intersects and forms the circle. In terms of map distortion or accuracy, tangent projections do not have any distortion where they touch the globe, and you can see in the image on the left, the further the surface moves away from the Earth, the less accurate it is. In secant projection surfaces, cylindrical and conical projections intersect twice, so they have two lines that are the most accurate, but they are closer to the edges of the map, with more distortion at the center and at the edges. In order to project an image of the surface of the Earth onto a 2D plane, we need a light source. The location of that light source relative to the globe is called perspective. The light source can be mnemonic, stereographic, or orthographic. Mnemonic projections have a light source coming from the center of the Earth. Conic and cylindrical projections are usually mnemonic because the results don't change that much, at least compared to planar projections. Stereographic projections have a light source on the point of the globe directly opposite from the projection surface, typically a plane. Orthographic projections have a light source located at an infinite distance directly across from the projection surface. Planar projections, and therefore stereographic and orthographic perspectives, are most commonly used to map the North and South poles and planar projections. Cylindrical projections are created when you put a cylinder around the globe, project the surface of the Earth, and then unravel it so it forms a plane. It creates a grid that has all right angles. However, in many cylindrical projections, like the Mercator, there is the most distortion the further you move away from where the globe and the cylinder meet. As mentioned in the video in the introduction, it's odd that cylindrical projections are so often used for wall maps, which make the poles look huge and changes the size of the more marginalized countries to make them appear smaller and therefore less significant. The video also mentions that even web mapping services use a Mercator projection, but at least they have some reasoning behind it. Conical projections are created when you put a cone around the globe, project the surface of the Earth, and then unravel it so that it forms a plane. When it's unrolled, the lines of latitude spread outwards and the lines of longitude become curved. Switch that. The lines of longitude spread outward and the lines of latitude become curved. I wrote altitude instead of latitude and I confused myself. Okay, the side of the cone towards the point becomes smaller and the side at the base of the cone becomes larger. Planar projections are also referred to as azimuthal, zenithal, and stereographic projections. They are created when you project the surface of the Earth directly onto a flat plane. In planar projections, the lines of longitude converge at the point or circle where the globe and plane meet. The lines of latitude form concentric circles. Planar projections vary most based on the light source that projects the map onto the planar surface. You can see the differences for yourself in the image on the slide. There are 4 types of map distortions, and it's impossible to have a map that's not distorted. The names of the distortions are based on the characteristic that is not distorted. Conformal projections preserve shape. Equidistant projections preserve distance, so that the distance between 2 points can be measured accurately. Equal area projections preserve the unit area. And lastly, equiazimuthal projections preserve angles, which allow for accurate directions. Maps can be equiazimuthal and either conformal, equidistant, or equal area. However, maps cannot be conformal and equidistant, conformal and equal area, or equidistant and equal area. Basically, if a map is not distorted in more than one way, it will include distance. All other combinations are not possible. In this slide, and the next 3 to follow, I'm going to show you maps of Tissot's indicatrices, or indicatrix in singular form. Tissot's indicatrices really would help me understand the differences between map projections in association with their different distortions. All projections start from the same surface. That surface is the globe. The globe has circles, all of which are the same size or area and therefore shape because of the geometry of circles drawn on it. Those equally sized circles are located along the lines of latitude and longitude at equal distances, accounting for distance and direction. These circle polygons are then projected, and each projection has its own Tissot's indicatrix because all projections are different. Otherwise, what's the point? So all these indicatrices show the circles were modified by the projection, how the circles were modified by the projection, allowing us to much more easily understand how the Earth's complicated surface becomes distorted. Apparently, I cannot talk today. In conformal map projections, the shape and angles are preserved. You can see in the image that the circles at the equator are the smallest, and they gradually get larger as you move towards the poles. Locally, or areas around a single point, have a constant scale. So small areas are represented accurately in terms of area, but larger areas are not as accurate simply because they cover more area, which makes them more likely to have a wider range of size values. Mercator projections are cylindrical and conformal, as I mentioned a few slides ago, as well in the video. In turn, conformal maps are infamous for fostering racism and white supremacy. I am trying really hard to not go down a rabbit hole, but I have to a little. Most land is located in the Northern Hemisphere. That land, the land that is in the Southern Hemisphere, not including Antarctica, more closely hugs the equator than it does the poles. In this particular projection, the smallest circles are at the equator. People tend to associate size with dominance or power. The larger size, the more power it has. This gives the impression that some countries are superior to other countries. When it comes to naming areas or groups of people, there is really no accurate way to do it. Over the years, I have heard groups called and characterized as things like developed versus underdeveloped, the global north versus the global south, Western versus Eastern culture. But what it all really boils down to in the end is race. Maps like these, the ones hanging in our schools and used in Google and Apple Maps, which are the ones we really see the most often, make white people look more powerful and important than other non-white people. I mean, just look at the size of variation in the circles when you compare the one over the Gulf Coast and the one over Alaska. That's nuts. Okay, jumping off my soapbox. Equal area maps have the correct amount of area or relative size or scale as the globe. In the image, you can see the circles changing from perfectly round to thinner ovals closer to the poles. Remember, if a map does not distort the area, it definitely distorts the shape. When I think of how equal area maps are formed, I think more about raster data, or pixels. Start with the blue square highlighted in the green on the left. That's our original object. It contains 4 pixels. Let's say each of these pixels is 1 square meter, which makes the original object 4 square meters in area. All of the rest of these groupings of pixels, or 1 square meter blue objects, equal 4 square meters when you add them all together. In any combination of the 4 pixels, so long as they are touching each other or are continuous, is going to equal 4 square meters. No matter how the shape changes the country on the map, the total amount of land is going to stay the same in equal area projections. Equidistant map projections maintain distance between 2 points. However, one point in that 2-point coordinate pair needs to be a point that was touching the globe when it was projected. All other combinations of coordinate pairs are not going to be accurate in terms of distance. Equidistant maps cannot be conformal or equal area, but instead they are a combination of both. Like with all projections, the further you move from the point of contact, or the equator in this example, the more distorted it becomes. You can see that in the picture on the slide, the original circles have become distorted in both size and shape. The size gets larger as they move towards the poles, like in the conformal projection, but they also change in shape, like in the equal area map, to form ellipsoids. Circling back, now we have geographic and projected coordinate systems. Geographic coordinates are the locations on the Earth's surface. They are measured by their degrees of latitude and longitude and are measured in decimal degrees or degrees minutes seconds. On the other hand, we have projected coordinate systems. Projected coordinate systems are coordinates that are located on the surface that you project the globe onto, or your map. These are going to have measurements of length. If you remember back to the slides on the grids and how the lines of latitude and longitude look, you remember that the lines of latitude are equally spaced and lines of longitude converge at the poles. Because the lines converge, the spacing is not the same everywhere, and that's a problem for taking measurements of distance and area. Imagine you are looking at a ruler. You have 12 inches spread 1 inch apart. Now, I ask you how long the ruler is. You tell me 12 inches. I tell you you're wrong. You're confused and probably wondering, why am I the one that's supposed to be teaching you? But I didn't give you all the information to answer the question correctly. Each consecutive inch mark has a written number next to it. Easy enough. But what I didn't tell you is that each of those number labels represents the number of inches from that line to the next. So the ruler does not represent 12 inches, but represents 78 inches. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 7 plus 12 equals 78. Now, you are not only questioning my ability to teach you properly, but also think that I need to have a long chat with my therapist about counting. Because distance measurements are not constant with geographic coordinate systems, you should not calculate measurements from them. Stick with your 12-inch, not your 72-inch, 12-inch hybrid magical ruler. And that's where I will leave you for today. Have a great week, and let me know if you need any help on your final projects or anything else for the class.